Branch Chair of IEEE IIT Kharagpur section. So today we have organized the invited talk by Dr. Francesco Fioranelli. He is from uh, DU Delft University. So I'll just briefly introduce him and then we can begin. So today's talk's title is Radar Approaches for Sequential Human Activity Classification. So Francisco Fioranelli, so he received his bachelor's and master's degree in telecommunication engineering from University of Politecnica delle Marche and Kona, Italy in 2007 and 2010 respectively. He completed his PhD degree in electronic engineering from Durham University, UK in 2014. So he is currently associate professor at TU Delft Microwave Signaling, Sensing Signals and Systems Group in Netherlands. Also, he was assistant professor at University of Glasgow during 2016 and 19, and a research associate at University College London during 2014 and 16. So his research interest mainly includes development of radar systems, automatic classification for human signature analysis in healthcare and security, drones and UAVs detection, classification, and automotive radar. Also, he has authored over 145 publications between book chapters, journals, conference papers. He edited books on microdoppler radar and its application, and also radar countermeasures of UAV. He published, which is published by IIT SciTech in 2020. Also, he received 3 best paper awards. So, without further ado, I request Dr. Francisco to continue with today's talk. I welcome you all. Yeah.
Okay, perfect. Thank you very much for the introduction and for the invitation. I hope you can hear me well and you can see the slides. Otherwise, let me know.
Yeah.
So in these slides, I will start with a couple of slides of introduction about our group here in TU Delft, just to give a bit of context, and then I will start with the topic, the technical topic, if you want, of the talk. You can see here directly in this slide our website, radar.tudelft.nl, and you can go there if you have more curiosities about who we are and some of the projects that we do. So this is just a slide about myself. You heard it a bit in the introduction. I've been here in the Netherlands since 2019 as first as an assistant professor and now as an associate professor, but I come from Italy, maybe easy to guess from the name and the accent. And I studied for most of my, let's say, professional academic career, if you want, in the UK, in different places. I know one of the previous talks in this series was given by Dr. Matthew Ricci, that was my colleague as a postdoc here at UCL together a few years ago. So nice to see that more or less the same people are working in this area of radar. This is just a few faces of the people here in Delft. We are the university is organized in different research groups. Our groups is called Microwave Sensing Signals and Systems. It's MS3 in short. There is a certain number of academics, then postdocs and PhDs, technical support, and a large number of master students, maybe 15, 20, 25 per year, depending on the intake that the university takes. Certain number of Indian students often is with us. And this is the number, by the way, not of the whole master students in the university. That's much larger. These are the students that do their thesis with us. And the thesis in Delft is about 7-8 months. So it's quite an intense piece of research. Our research is often very much anchored to experimental data, or at least to the use of some experimental facilities, which is something also that we're quite proud of, to have these facilities. You see here a few of them. There is an anechoic chamber with dedicated equipment. There are radars that are designed for long range detection. So we have here, this is a roof, even if it looks like a ship. It was actually a very foggy day. So these two radars, Parsecs and Heavy, are on the roof, the building, and then there is a new radar that's called FARA that will be built in a couple of years, 2-3 years. They all work at different bands, S band, X band, and KA band. They're all, let's say, have polarimetry and in some cases for FARA phase array capabilities. So we're really looking forward to see what we can do with this new radar. Apart from the long range, we also have, of course, short range radars, which are actually more relevant to the talk today. So here you can see a picture of the lab where we have 5 of these relatively old, but still alive and kicking pulse-on radar that can be synchronized with each other, and all other types of radars, millimeter wave radars from Texas Instruments, maybe very common in the literature these days, and some other ultra-wideband radar, and many more. Now, that was a, let's say, 2 minutes pitch about Delft. And of course, if you have questions later, feel free to ask and or send me an email for questions on that. And now we start a bit with the topic of today, which is the human activity classification. So typically, this idea of classifying what a person is doing when we use radar is very much linked to the concept of microdoppler. Maybe this is a concept that is familiar to some of you, maybe not. So I'll just give a quick recap on it. So microdoppler is a concept that was let's say, formulated and explored first by Victor Chen, which is maybe the person that everyone associates in the radar community to the concept of microdoppler, and his collaborators. So here you see the definition that Chen himself gives about this phenomenon, and I'm just going to read it just to start up. So it's basically the intricate frequency modulation that is imparted on the backscatter signal by the moving components of a radar target. So if we want to sort of break this definition into pieces, we can start to focus on different aspects. So the first and most important part is that this phenomenon, microdoppler, happens when an object or a target, let's say, has moving parts. So it's not, let's say, a single body that is traveling with a certain velocity that will produce a certain Doppler, but is an object that is composed or has parts that move. So we can think of, for example, parts that can rotate, vibrate, oscillate, or swing. And these multiple body parts or target parts that will move will generate extra Doppler modulations, extra frequencies that are on top of the normal Doppler shift that an object will have while moving. We can think of a simple example of a helicopter that, for example, is flying in a certain direction. There will be a total Doppler given by the overall motion of this object in a certain direction. But because the helicopter has 2 rotors, those are 2 moving parts that are rotating, and those rotors will induce in the radar signal that we receive extra modulations. This is what we call the microdoppler signature of this object. Now, one thing to notice is that this word micro doesn't, we have to be careful not to be deceived by this word, because it's nothing to do with the extension of the movement or to the amount of the Doppler shift that we are measuring. Again, back to the example of the helicopter, the microdoppler is caused by a large part. So the blade of the main rotor is an object that is very large, so it's not micro at all. And depending on the carrier frequency of your radar, the microdoppler signature can be high in terms of hertz. So it can be tens, hundreds, or even more, even in the range of kilohertz. So if we want to sample the signal properly, we have to be mindful in a sense of all the consequences in terms of, I don't know, ambiguity, or in terms of the requirements that the analog to digital converter at the receiver of the radar will need to have. So although it's called microdoppler, can be caused by big things and can be a big signal in terms of frequency. Here I just put a few books that in the past have been published on this concept of microdoppler. Some are more, let's say, theoretical. So the book by Victor Chen describes the phenomenon. Other books here are sort of a bit of a catalog of applications and techniques in different areas of microdoppler. When we look at, so that was the phenomenon. Now we are, as engineers, as scientists, we need some tool to describe and to use this phenomenon to our advantage. So typically in the literature, you will see that the microdoppler signature, so the microdoppler modulations associated to a particular type of target are studied with a spectrogram. A spectrogram is essentially the absolute value, or the absolute value squared. There are both definitions in the literature that result from the application of a short-time Fourier transform. So what is a short-time Fourier transform? Is essentially a Fourier transform that is applied with a sliding window over a signal, because the signal that we're looking at is a non-stationary signal. What does it mean? It means that essentially the frequency of this signal is changing over time due to the different velocities and motions of the body parts of a target. So the flow of thought goes this way. We have a target that has moving parts that over time move with different velocities. All these different velocities will be translated to different Doppler frequencies, and the pattern of these Doppler frequencies over time is what we want to study and what we can visualize with a spectrogram, for example. So you see here an example of a spectrogram of a person that was walking towards a radar in an outdoor scenario in a field. And this is, let's say, the typical spectrogram, radar spectrogram of a person walking, because we see, let's say, a central contribution, which is stronger in intensity due to the torso, so the body, main body, if you want, of a person. And then you have all these sort of blue, light blue in this case, streaks, positive and negative, that are due to the movement of the limbs, so arms and legs of the person as the person was walking. Then you see here at 0 Hertz. 0 Hertz means nothing is moving. This is essentially the contribution of the clutter, so the stuff, the field, the objects in the field of view of the radar that were not moving. What is important here is that we're looking at a pattern of Doppler frequencies over time. Now, what do we use it for? So if we want to use this information in a typical classification pipeline, more or less, if you look at the literature, you will see something that looks like this. We always start from some data, either by collecting it with experiments. Typically is actually students like most of you in the audience that are asked by professors or researchers to go and collect some data, or we use simulations, so a certain model that represents the behavior of a target. Then we have some pre-processing on the signal. The short-time Fourier transform is only one of the techniques that have been proposed to study non-stationary signals over time. There are many more. Then we can extract some features, so some units of information from the signal, and then we apply a classification algorithm to try and teach, in a sense, an automatic algorithm to differentiate one type of object versus another. Nowadays, it's been a few years, of course, there's been a great advance in artificial intelligence, in particular deep learning. So these two steps of feature extraction and classification are actually typically merged into different types of neural networks that can do both jobs. So you don't need, let's say, a human decision to say which features to extract, but somewhat the neural network learn what is important, where is the information in your data. And if you look at the literature, actually there is a debate, a discussion, or an exploration on whether also some of these steps of more classical signal processing, for example, making a Fourier transform or making some denoising of the data, should be done by the network or not. I'm not entering into that now because it's a long discussion, but just to let you know, let's say that this 4 steps, if you want, of this classic pipeline sometimes can be compressed in a sense that this red part is more and more assigned to artificial intelligence techniques. Now, the problem that we're looking at is the problem of looking at what people are doing in an indoor environment. This area of research started, maybe, I don't know, 10 years ago, something like that, with a specific application in mind, which is fall detection. So in particular, especially in, let's say, Western countries, but also, I don't know, United States, but also China, population is aging. There is a large number of people of older people or vulnerable people that are living alone, and falling is one of the leading causes of problems for the older population, for all the bad consequences that fall brings with that. So a lot of technologies have been proposed and validated to try and detect automatically whether someone has fallen in their room, and they cannot ask for help because they can't stand on their own. This is where we started, but then in a sense the research has expanded to try and look more comprehensively to the pattern of activities that people do in their environment, because from the pattern of activities, perhaps some anomalies, some changes in the way the person behaves, in the way the person works, those can be proxies for healthcare professionals to understand whether the person health has some incoming problem. The golden egg there is always to try to catch these health problems, to prevent them before they become so serious that the person needs to be hospitalized or requiring some intensive care or some expensive also type of assistance. So from fall detection, we moved, let's say the research moved to classify different activities. And here you see an example, some 6 activities that were collected some years ago by a student of mine in Glasgow. These are spectrograms, so what we look at Doppler or velocity, if you want, on the y-axis, and then on the x-axis we have time. Now, these activities initially were collected as a snapshot, as we call it there. So there was one data recording, there was only one activity there, then the person stopped artificially and then did something else after some time. So it was a very, let's say, non-realistic way of the person to move, because each image represents one activity, but that's not the way, of course, people in reality will move in their homes. So people in reality moves as a sequence, so they do one activity after the other, and there is no way to know, in a sense, a priori, what the person will do and when. So we call this continuous sequences or continuous activities, because the activities come one after the other, and there is no guaranteed in when a transition between one and another will happen or not. What you can see here, you can see one example again of a spectrum of 6 activities that you see here, and below here you see 3 examples of 3 sequences where the activities were the same in a sense, but they were swapped in order. So a person did the same thing, but did them in different orders. So if we want to classify type of data like this, now we have one sample, one recording. We decide to look for a certain duration, but we have a number n of activities inside there that we don't know. Problem is a little bit even more complicated, because these sequences can be extremely diverse as well. So this is the first example where we collected some years ago in Glasgow. We partnered with a housing association which hosts older people. It's called North Glasgow Homes, and we asked all these different people to do the same sequence of activities. You can see here that although the people are asked to do exactly the same sequence of movements, depending on the gender, on the age, on the physical condition of the people, the patterns are very different from each other. But if you train, let's say, a classification algorithm to recognize this, you would expect in the ideal situation that the answer is the same, because the people were asked to do So any, let's say, algorithm that you develop has to be able also to deal with this large diversity of the data between one person and another. The diversity can also come from other aspects, which is, for example, where you locate the radar or your sensor with respect to the area that you're trying to monitor. So here is an example. Again, this is our lab in Delft. You see here two spectrograms recording at the same time the same sequence of activities that the person was doing in this area here. One is radar 1 that you see on this side of the room, one is radar 5 on the other side, so they are kind of facing each other. So in a sense, the Doppler can change quite a lot its sign depending on the direction that the person was moving at in that location. So if you want to try, let's say, and combine the information from these two, you have to be mindful in a sense that the different radars will see a very different Doppler signature, although there's only one person doing activities. So it's in a sense diversity to manage in a different context. This is again another example of a spectrogram in Delft, just to give you another view of how different, in a sense, spectrograms for different people performing the same activities, but at random times and in random trajectories can be. So this concept actually is a bit more general, so we could, let's say, think that the challenges of managing this type of data actually are not there just for activities, but we can consider, for example, gait, so the way people walk. We can debate whether gait is an activity or not, but sometimes in the literature you see papers that deal only with gait analysis with radar rather than activities. More interesting, the gestures, so human gestures that can be used for interaction with smart devices, but also sign language, so gestures that actually have a much more important meaning because they actually mean words. And you can see here an example where there were some body activities, sitting, for example, or standing up, completely mixed, interspersed with sign language. This was American Sign Language that meant these words here. Of course, you put also vital signs in the picture, because you could imagine that when the person is not moving too much, where it's relatively static, you could also do some analysis of the respiration, of the heartbeat, and so on, to see whether there is any anomalies or any problem in there as well. This is an example again of a spectrogram of respiration, and the case of apnea here, where there was no respiration. So in a sense, this concept of a long stream of data where a lot of things can happen can be generalized not only to activities, but also to gestures, to sign gestures for deaf users, and also to vital signs. So what are, in a sense, the characteristics of things that we should be looking at? First of all, as I said, they are continuous, so they are all activities or classes that we want to differentiate are happening one after the other, and there's no constraint in how long they should last and where or when one should start or stop. There can be misalignment. So in a sense, it's hard to define when a particular type of activity is starting or stopping. If you think, for example, of the movements that you do when you are working and then you decide to sit down on a chair, it's very hard if we want to say, okay, when did the movement of sitting started? So it's there can be some misalignment in deciding in the ground truth where one activity starts and when the other begins. There can be interruptions. So in a sense, if you are looking after you have trained a classifier at its performances, you could have some situations where the prediction of these classifiers fluctuates. So you have some outliers that in a certain sequence tells you that all of a sudden the person did something else. If these outliers are very, let's say, sporadic, you could sort of say it's impossible that the person is physically, kinematically impossible that the person did that action. But if you are too strict with this rule, you might have the risk that you actually miss that activity that the person was doing. So being mindful, let's say, of the kinematic of the object that you're trying to study is also something important and has to do with this aspect here. And then finally, there is an important aspect, which is the fact that of the imbalance of the data sets. If you remember, I started saying that this area of research started to look at fall detection, so a very critical event that doesn't happen too often, luckily. But then how do you train, let's say, something to classify this object, this event, if you are not in the possibility to get a lot of samples, a lot of observation of this event? So this is an important point to consider when you decide, let's say, what strategy in terms of machine learning and algorithm you want to apply to catch these critical activities, of which unfortunately you don't have a lot of samples. Now, how did people, let's say, in the literature, in the recent literature, looked at these continuous sequences of activities? The first, maybe most simple or silly, perhaps, approach is that, okay, you force this activity, this long sequence of activity, to be to be non-continuous anymore. So you apply a sliding window and you classify by sliding window to sliding window. So here, this can work because then you reduce, let's say, your sample, your long sequence to a series of snapshot activities, snapshot spectrograms. But then you have the problem that the duration and the overlap of these windows are extremely hard to estimate a priori. So which window should you use? And the answer depends also on the velocity or the level of activities that the person is doing. So establishing, let's say, a priori a window that works for every situation, it's not possible. Another example of technique or a family of techniques is to use to change data representation in a sense. So to use perhaps representation of the radar data that are by definition, in a sense, split into discrete sequences. For example, if you think of modern millimeter wave radars, so if you buy, I don't know, Texas Instrument radar, just to mention one that is typically used in academia, the way it works is that every X seconds it will give you a frame, so it will give you a unit of data. That the unit of data, which we could call a radar cube, you can extract, for example, a range Doppler, and then you have a flow of range Dopplers one after the other. So in a sense, the way the radar is constructed does the segmentation for you. So you have directly from the radar a flow of sequence that is a flow of data that is already discretized over time. So in a sense window. You could apply a classification technique that works on each specific data output, so in each specific radar cube or range Doppler frame, and then maybe use a techniques that combine the predictions from each of these radar cubes. And we will see later another example. Here, the example that I give is not so advanced, but it's a prediction that happens at each range Doppler image. This concept can be sort of expanded. So I'm just going back to the previous slide. Here we are, let's say, classifying on a 2D structure of data that tells us the distance of the person and the Doppler. But we can add also some time by looking at how pattern extracted range Doppler by range Doppler changes over time. And this is, so we add the third dimension, if you want, we take back the dimension of time to link each frame to each other. This was actually a piece of work done by some collaborators in Nanjing University in China, where they built this sort of trajectory in the range Doppler time to identify, for example, if there was a fall you see here in blue, there was some kind of high Doppler expected, so this normal trajectory in a sense that the normal pattern of activity would do can be differentiated from where there was a critical event, because the trajectory would change quite. It was quite noticeable, let's say, how the trajectory would change. As I was saying earlier, recently, neural networks come to give us a lot of extra tools. So one natural investigation was to say, okay, if I go back to my spectrogram and I have a sequence of Doppler patterns, Doppler values over time, I will consider each time step as a unit of information that I give to a recurrent neural network. So it could be an LSTM, it could be a GRU and their variants. So what this network will do is giving you a prediction, in a sense, every time step, and that is, let's say, the result that you use. You see here an example of a sequence that provided a very good result. Unfortunately, they were not all like that, apart from some little delay between the ground truth and the prediction. But in a sense, the network was always, in a sense, correct in this case. This approach can be generalized, because you can think, for example, that in a smart home you don't have only a radar sensor. You might have various sensors that are combined together to provide a better monitoring capability of the person. This is sometimes goes under the name of multimodal sensing, and each sensor will provide information over time, and you construct, let's say, this type of recurrent network that can process all this information together. In this bit dense slide, this is what I show you, where we try to combine the spectrograms from the radar with the information that came from a wearable sensor at the wrist of the person, which had an accelerometer, a gyroscope, and a magnetometer inside. The results are here in this colorful picture. Here we have 15 participants who were performing certain sequences of activities, and the blue columns represent the accuracy if you use only the wearable, whereas the other colors represent, let's say, the extra capability that you could get if you combined the wearable information with the radar information with different, let's say, strategies of fusion. And you can see that in general, for every participant, some more, some less, you get a boost by that, especially in the situation where the wearable was not providing very reliable data. This is another example of the same story, where the sequence is a sequence actually of gates. So this is a long sequence where the person was asked to walk in a circular trajectory, let's say, in a lab, and change the way they were walking. So normal walking, simulate dragging a feet, simulate to have very small steps, and so on. And the idea is always to try to combine in this case, not radar and wearables, but information from different radars. There were 3 radars looking at the scenario that were combined together. So in terms of what is in common between this slide and the previous 2 slides, just to summarize, is the fact that you sort of are using your data, so your spectrogram, so your pattern of Doppler over time, as the input to a recurrent neural network that by definition will be able to provide you a prediction for every time step and for every unit of information that you provide. This example from the previous slide is also handy to show us some of the things that might not work very well when we try this approach on the spectrum. So for example, well, the first problem that can happen is that there is a mistake. So here in red, your network, for some reason, gives a wrong classification. So the ground truth here was supposed to be gate number 2, and the network said gate number 3. There's not much to do there. It's a mistake. and the network was quite confident because it really never changed its mind. It's really different. In green here you can see something a little bit different, where there were some oscillation here. So there was some sort of back and forth between the wrong prediction G2 versus the ground truth in G3, and then at the end the network decides, let's say, for the wrong situation. But there are cases where there is this oscillation between the two activities. Then you have here an example of misalignment, we can call it this way, or delay in a sense, where the network gives you the correct prediction. So you see that the blue converges, overlaps with the red, but with a certain delay. And here, the potential issue is that, okay, do you consider this, let's say, a mistake or not? Because in a sense, the network eventually gives you the correct prediction. It tells you that this event G2 happened, but with a certain delay. The problem is also your ground truth is not 100% reliable, because deciding where, as I was saying at the beginning, one activity A, class A, starts and activity B finishes is not black and white decision. So we have to be mindful, let's say, of how to evaluate the performances of our classifiers in the presence of these events. As I was saying earlier, actually, to the best of my knowledge, approaches that are out there in the literature on this topic are the ones that combine both worlds. So you have, let's say, a network or a classifier that looks at an image-like or 3D cube type of data, so typically a CNN at the moment, convolutional neural network with various characteristics, followed by a recurrent neural network block that takes into account the temporal relation between these blocks. So something that sort of takes the best of both worlds. Here I give you two examples. One, this is actually from one of my former master students, now PhD in Delft. So we used, let's say, CNN blocks and then recurrent bi-GRU network here. And this is from the literature, where they used also 3D CNN, and then they used LSTM blocks. These papers are a couple of years old, so not the newest of the newest, but you, just as information, you might have heard that typically now recurrent neural networks can be superseded by transformer and attention-based architectures, but the principle can be applied equally here. So you have an initial block of feature extractor from your radar data, and then you have the transformer unit that takes into account the temporal aspect, so the link between each information. I think this paper here on the right-hand side was published, in 2018. It's quite interesting because what they do, they also add an extra layer at the end here, this CTC, connectionist temporal classification, which is actually the right tool, in a sense, to deal with those events of misalignments and oscillations in predictions that you might have at the output of neural networks. So you have a tool, let's say, with this CTC that can take into account, that can smooth, in a sense, the predictions at the output. More details are actually nicely explained in this paper here, so you have the references, and you can go there if you are particularly interested in this topic. In the literature, you also have, let's say, different approaches where you take a step back and say, okay, I don't want to put all my sequence into complicated network that is made more or less by CNN plus LSTM, but I want to apply a segmentation of my sequence according to certain criteria. What is the rationale of this approach? The rationale is that human activities are very diverse, as I said, the beginning sequence. So there could be a certain interval of time where the person did many activities. I'm thinking of myself earlier. I stand up, I go to the coffee table, I make a coffee, I make a phone call, I move a lot, and then I sit down here. Maybe I read some papers, but I don't do much. I'm quite static. So having a sliding window or processing all the time steps in the same way with a neural network without being mindful of what the person is doing might not be the best strategy. And this is what these segmentation papers are trying to say. What is where is the problem here? To try to find a descriptor of the signal that can give you a good information on when one activity is present or when another activity is starting. I give you here some names and some papers. I don't have time to go into a lot of details, but the simplest one was simply to calculate some kind of power estimation, power burst that you have on the spectrogram. But there are more advanced techniques now, like some kind of double average on short and long terms that are compared to each other, and also some forms of entropies that try to calculate how much information there is over time in the signal. These are just examples again from the papers below. Maybe you remember this sequence with human activities and American Sign Language, and you can see here how the authors have applied STA, LTA to this data to identify, okay, where each segment of spectrogram should be sort of cut and then processed and classified on its own. It's a slightly different approach from the previous ones that I presented, because here we go back to some sort of windowing, but it's a windowing done with a certain criterion. So the criterion given by this metric and not just a sliding window that is fixed. Now, I touched earlier on the fact that there can be these misalignments and these interactions, and especially imbalances. So one can ask himself also what are the metrics to take into account these events. There were in this paper, actually one is a paper from my student, but there was also a couple of papers from a group in Chengdu in China that looked at that and tried in a sense to take intersection over union metrics rather than the classic accuracy or F1 score to classify, to assess the accuracy or the performance of the predictions. So the idea here is that if you have, let's say, a ground truth where in all these time steps, which you can think these are time steps of a spectrogram, always activity A is present, but then in your prediction, you have, in a sense, some interspersed segments in green here that are not classified as A, how to penalize, in a sense, how to be strict on the fact that you have these events. And here there is no, let's say, right or wrong. There is, let's say, maybe a discussion to have when someone presents a paper or results of how these events have been dealt with. Because it might sound, let's say, a very academic discussion, but imagine that, for example, this blue activity in the ground truth is working, and this green extra samples that you have in the prediction are, for example, labeled as fall. You have to be very careful in which way you go. So do you consider that as a fall and therefore raise an alarm after, let's say, believing the radar sensor, or you think that this is not cannot be a fall because it's only one segment? So that is where, let's say, the definition of the metric is where the definition of the metric, let's say, is related to actually an operational concept. So as I say here, it's not black and white, but it's in a sense a discussion, an observation in depth that would be nice to have when people work in these areas. Now, oops, something happened to my keyboard. I'm sorry. I'm back here. So to summarize, where are we in terms of challenges in this topic in general? So of course, the general challenge I described is that we are dealing with arbitrarily long, continuous and diverse sequence of activities where you have all sorts of types of movements, from the very large ones when the person is walking to the very small one, for example, the respiration and the heartbeat when the person is static. Plus, all these sequences are very different from one person to another because of difference in physical characteristics. Then, of course, you have a problem, general problem, because we are trying, in a sense, to approach this with the tools of machine learning or artificial intelligence, and therefore we need a lot of data that has to be reliable and labeled. And where to get this data is not easy, because unlike cameras maybe or wearables, there is, to the best at least of my knowledge, not a large data set that every scientist in radar says, okay, that's the one to use. One problem is, which is not only limited to these applications of radar, it's a problem in any, I would say, in any field where we use artificial intelligence, in particular deep learning, so neural networks that are difficult to explain, is indeed how to make our algorithms explainable and interpretable, so that we know why a certain prediction, why a certain decision has been made by the algorithm. There is a lot of discussion. There are some techniques that are trying to make try to answer this question. So how we can explain why a neural network took a certain decision, but it's certainly, I would say, not a solved, not a 100% solved problem. Then there is this is a bit more radar geek challenge, but I mostly talked about spectrograms in this presentation, but that's only one form or format of the radar data. You can take radar data in many other information. So, for example, millimeter wave radars today give you the so-called point clouds, where you have, in a sense, X, Y, Z, the coordinates, the Doppler, the RCS of the points. So how to exploit this multidimensionality in the data that goes beyond the Doppler and time? Good question. And then if we think broader than radar, there are many other sensors. So how do we combine the information with from these other sensors with the radar data that we get? So which are the best fusion approaches and policies to combine multiple data together? I mentioned earlier that one issue for that the radar community is looking at is that the fact that there are no shared data sets to develop classification algorithm, at least in this context of human activity recognition. But you see that every group tends a little bit to collect its own smallish data set and work on that. The situation is slowly changing. People are starting a bit to share their data. We are trying to do our part. So at this link, this QR code, you can download our data set that we collected here in Delft, which is interesting because it's made with 5 radars that record simultaneously the person. So in a sense, it's interesting because then you can compare and fuse the information from the different radar. The link is there, it's publicly available for anyone. And that brings me to the end of the presentation. I thank you for your attention, and I also thank all the students and collaborators, because a lot of the results shown there come from there. So if you have questions, feel free to ask.
Yeah. Thank you, Dr. Francisco, for such an informative and yet concise lecture. So I request attendees to ask questions. So Pallav Gogoi, I think you want to ask a question. Can you go ahead?
Yes. Am I audible?
Yeah.
Yes. Yeah, thank you, Professor. It's indeed a great presentation. So I had a few queries regarding the hardware. If you could just answer this part.
Yeah.
So the question is like the hardware that you were using for your radar, is it like it's like some commercial available, or like the radar hardware that you have built it by yourself?
Yeah, thanks. Most of the, actually almost all the spectrograms, all the data that you see is commercial hardware. I will go back to show you some examples. So, for example, these ones that we collected in Glasgow, it
Yes.
was a radar called from a company called Anchortech, which I believe is no longer in business, but there is another company which I forgot the name of that can sell their hardware. So this was a C-band FNCW radar. The Delft, let me go back to where I show you the Delft radars are typically this pulse-on radar, and these are pulse radar, pulse ultra-wideband radar that operate around 4 gigahertz, so relatively low frequency.
Mhm.
And you see here other radars. So these are called Xitru, and these are X-band ultra-wideband radar, and these are millimeter wave from Texas Instruments, so 60 gigahertz or 77 gigahertz FNCW. So in general, we tend to use for this type of short-range research commercial radar.
Yes, yes, and then second question, just one more question I have, final question regarding this. So when once you have this radar, so regarding there were two issues normally. One is the IQ imbalance, in phase and quadrature phase imbalance. The second is the DC offset. So is it that you do something in the hardware level, or like you do in the signal processing? And also when you take the spectrogram of the micro Doppler signal, so there are a huge amount of noise that is there. Like the signal is not that clean. What we have seen. So you use any noise suppression algorithm before getting the spectrum?
Yeah, very good question. So let's say our policy so far has been to, in a sense, accept the quality of the radar data as it comes from the commercial product. So if it's noisy, or if it is, let's say, imbalance in terms of INQ, then we accept, in a sense, that we cannot do anything in the hardware itself, apart from maybe telling the company, if it's a partner, please do something. But so most of the actions that we do are in signal processing. So if there is noise, we try to apply some denoising. We try to see whether we can sort of isolate a little bit the signal component from the clutter component, because in general, let's say, the objective that we had so far as an academic group is to provide, let's say, a proof of concept, no, for an algorithm. So as long as the data are okay, so there is some signature, we were and we are happy with that. Different is the question if you say, okay, should we deploy this into a real environment? Then this is a question, this is an important question, because in that case you might need maybe to spend a little bit more time to do some proper radar design. So you really need to worry about, okay, but what noise figure, I don't know, or what sensitivity do I really need? Problem with that is that RF design is a discipline that is tough, and not many students, at least in this part of the world, are able, or but not because they're not able, because there is not so much, let's say, teaching in this direction. So finding a PhD student or a postdoc or someone that can do high quality, let's say, radar design, is very hard. And I think if there is a person that can do high quality hardware design and a bit of radar signal processing and a bit of machine learning, that person will probably go to work for a company for a much higher salary also than what I get. So you know what I mean? Just I went a bit off road, but for the purpose of academic research, we sort of say, okay, we take the low risk road of taking whatever the commercial radar can give us, but we But if I don't know, at some point someone says, okay, let's deploy them in really the quality of this sensor.
Yeah. Yes. I hope you answered his questions. And
Hello, sir.
yeah, so
Yes, yes, indeed.
yes. So actually, I have one question related to the same slide. So as you have
Please.
mentioned, there are multiple radar modules which are being used to collect the data set with different aspect angles. So, like, have you considered the effect of change in polarization because of the polarization change of these backscattered signals? And what it,
Um,
yeah,
yeah, thanks. It's a very good question. Actually, it's an aspect that it's much explored in the literature, at least for human activity recognition. So we haven't. That's the answer. We haven't really worked so much on looking at what happens if you change polarization. Um, it could be interesting to see. I think human target is, in a sense, by definition, more vertical, let's say, than horizontal, the way we are built. But it could be that when, for example, the body takes an horizontal position or moves in certain directions, that there could be a polarimetric effect. So um, it would be interesting to do this, and yeah, why not? But we haven't looked at that so much.
okay,
One difficulty is that finding good quality polarimetric radars is difficult. You don't they're not easy to buy around, um, and then guarantee in a sense that the polarimetric purity between the channel is high enough so that any difference that maybe you see is due to the object and not due to some artifacts in your radar itself. But theoretically, I would say it's a nice direction to explore.
okay, okay. Thank you for your comments. So yeah, I
Hello,
guess
can
yeah,
I ask?
yeah. Go ahead.
Yeah, yeah, that was a great lecture, sir. I have a simple question to ask. I mean, like, how to differentiate different micro Dopplers without knowing the knowledge of the target. I seen the slides where you have mentioned that one is sitting, standing, or moving, something like that. I hope that they are categorized there because you knew the target how it was moving at that time. I hope so. That's
Um,
how it. But how to know without knowing the any knowledge of the target? How to, let's say a person is handshaking and a person is moving. Both looks they look different, but how to differentiate which is what? Is there an algorithm or kind of something? I mean, like how to differentiate? That's what I have been.
Yeah, thanks for the question. I think maybe the presentation, let's say, doesn't show the full pipeline, in a sense that before you go and extract the microdoppler, you would do a step of detection. So you would look at whether there is a target at all, and how much, let's say, Doppler in general you have in the environment. So
Yeah,
is there something moving? And only maybe when you see that there is
yeah,
something moving, then you would kick in, let's say, the microdoppler
yeah,
processing,
yeah.
in a sense.
Yeah, yes. I mean, like, let's, we can say the micro Doppler signatures are there by after extracting the image, but to classify them, we have to know what is that what, right? At least to give the labels to them, like it is a standing movement and it is a walking movement.
The,
Without knowing,
the
is there anything like that? Or,
the labels, so when we collect the training data for the labels unfortunately are either given, let's say, by by the humans that prepare the
yeah, yeah,
data,
exactly,
or
sir.
we use, let's say, some form of transfer learning from a camera. So we take the camera and
Yeah,
radars are synchronized. The camera
yeah,
is
yeah.
reliable in a sense on giving you the labels,
Go.
and then you transfer those labels to the radar data.
Yeah, yeah. Thank you, sir.
Yeah. Okay. So we have one last question, sir. So uh, Anur Arvind Kundu, he is asking, is it CW or pulse radar, and what kind of signal is being developed, chirp or any other signal? And the second question is, what is the typical transmitted power level in this system? So I
Yeah.
think it's related to the system.
Yeah, thanks. Regarding the first question, the results that I showed are a little bit of mix and match of both pulse radar and CW, actually FNCW radars. So in a sense, you see in the literature both types of modulations, so a pulse modulations or a continuous modulations being used for these applications. So in general, I would say this is maybe personal opinion that there's not much difference in a sense that you can do you can, let's say, approach this problem with both types of technologies in terms of the signal that you get back. In terms of the power level, yeah, I don't have the numbers at the back of my mind, but at least in our work, these are very low in a sense that we never add amplification stages or anything that what the commercial sensor would give you. So I would say for sure below 1 watt. Then each different radars I showed you earlier has a different level of power. Sorry, I don't remember the, the numbers from the data sheet, but whatever these commercial radars gave us, we took in a sense, and we modified the setup to make sure that we could see the target.
Yes, yes. So mostly it depends on the module, which module you are using.
Yeah, depends on the module. Yeah.
Yeah. Okay. So I think we can conclude. Ritesh, do you want to ask any question?
Yes, yes.
Yeah.
Sir,
Please go ahead.
thank you for the great session. Sir, I have a question related to fall detection. So, when we are detecting fall, so there may be some activity that replicate fall, like when we are sitting very fast on a chair or on the ground. So, I think that may generate similar signature like fall or other activities which follow fall like signatures. So how to deal in that case if I want to means classify only fall?
Yes, you are really touching on, let's say, one of the big problems, the fact that if you are moving with a fast acceleration downwards, that is the best way to create a false alarm for fall. And in a bit, in a sense, it's also what complicates the use of wearable, because the wearable will see, okay, there's a big acceleration, and that will cause false alarms, right? How to deal with it? I think you have to well, first of all, I don't have, let's say, a solution that I can say, okay, I bet all my money on that and that will work. But I think that you need to try and exploit the diversity of information that new radars can give you. So for example, when if we think of radars that can give us a point cloud, so a sort of course at the moment, but in the future probably better when the radar chips become capable of having better spatial resolution, you get a sort of profile in a sense of the posture or the body shape. So the information that you will use to take a decision is not simply Doppler or velocity based, or there's only, there is a an acceleration or a velocity going downwards towards the floor, but you also get a bit of spatial information to support you to the fact that, yeah, the person is still sort of not completely lying on the floor, for instance. How easy it is to do what I just said, I don't know, but I would say that is, let's say, the direction that I would try to look at if, I don't know, a student would like to say, okay, I really want to explore aspect of false alarms. But it's a very good question. That's why in the data collections, people always put, sitting, bending, squatting, this type of activities that are that can create false alarms. Then, if I may, also a side note that when we think of data collection, let's say in laboratory conditions, typically the volunteers that are recruited are students and or academics that are not too old, like myself, and these people move a little bit or sometimes much faster than the actual end users. So some years ago, I actually asked my parents to be my subjects. My parents were back then, I don't know, 60 something, and I can tell you that when they sit down, or when they squat, they move much slower than my PhDs. So we also have to be mindful in a sense of the difference in kinematics between healthy volunteers when we trial these algorithms and the actual end users. So I'm not saying that the problem of fast sitting or fast squatting is not there. It's definitely there, but it's important in a sense that we fine tune in a sense the algorithms to know the average, in a sense, velocities of the targets that we want to monitor.
Okay, sir. Thank you, sir. So one more question. So in that particular slide, you are using 5 sensors.
Yes.
So are they operating on same frequency?
Yes, they are operating in the same frequency, but they have a modulation, some kind of coding in their waveform so that they can operate simultaneously without interfering with each other. And this is actually what made, let's say, this product, which is now a little bit old, attractive, because you could have these radars operating at the same time without a hard synchronization with wires, etc.
Okay. That's what my question was, whether
Thank
there is
you.
any interference or not.
Okay.
Okay, thank you, sir.
Thank you, Ritesh.
Thank you.
So yeah, we come to the conclusion of today's talk. I thank all the attendees and for all the questions and discussion, and also I want to thank Dr. Francisco for his time and accepting our request. So it was great to hear from you, and we hope in future you'll visit our university in India. So yeah, have a great day.
Thank you.
Thank you.
Thank you for the invitation and for your questions.
Yes.
Really nice.
Yeah.
Thank you
Thank you
very
all.
much.
Yeah.
Thank you. Bye-bye.